smooth space. Then we'll define this relative to our homology. Just as usual, as package homology of the motivated ground complex. And the remarkable property is that this is a quasi-coherent sheet over S, and it has an integral connection. So Gauss-line connection. Identify, well, infinitesimal those fibers of this sheet. So you can say that, oh, you may take some base S, you may take some point in it, and some tangent vector. So a tangent vector is just a morphing from spectrum of null numbers to our scheme. So, well, if you restrict your module connection on this infinitesimal scheme, this will just give a generalization of this point. So, namely, it will give an isomer HM Durand of x over k of epsilon. Just well, it's a module for this flat point, and it says that this family is just trivial. It's only to a special fiber. It said that ground homology to form trivial. Well, also, and Grothendieck invented an upgrade on this construction. So let me first formulate it, and then I'll explain why it's a right now. Theorem. Yes. So I will write it in a 1 per kilo pace. Actually, I think that's the most important. So it says that there is a function. It's the homology function. Say from the category of let's say smooth schemes. Over FP, filled with periods. To the just complexes of 0 and direct. Yes, and there's function has the two main properties. So first of all, is that it lifts the wrong homology. It's canonical because it's homomorphic, or its reduction of P. It's canonical because it's homomorphic to the Durand. Yes, and the second one is that if a scheme X over P actually lifts to 0 European, if it's a smooth scheme, well, it's special fiber is RS. Then there is canonical quasi-isomorphic. There are homology this theory tells us that though schemes over FP or a scheme over FP don't have any liftings at all, or it may have many liftings. So however, anyway there are no canonical liftings. But it says that the round homology needs a canonical lifting. Yes, and so in what sense it's related to the story of connections? Well, it just says the connection says that if we already have some information, then so this analogy is just a particular case. So it says that just if we have some information, then the wrong homology of this information actually depends on the wrong homology of the special fiber. So it doesn't depend on the information. This theory just generalizes. So you may ask why I pick a field of positive characteristic here. Well, the thing is that if instead I would take say Q, I need to take something. I first need to deform the base. So take something instead of this. So if I take a field of zero characteristic, then this deformation has to be an algebral derivative. So there only exist things like Q, say X, or X1. And so this actually needs a section. So over side base, you always have a trivial deformation. So at least you have a candidate for this for the value of this function, just the ground homology of a trivial deformation. And if you work, but if you work over FP, then we have this deformation of the base, which is closed plate. So there are no such notion as a trivial deformation. So in a sense, well, this is a most difficult picture. Okay. So this is the connectivity part, and now I wrote in that that I want to generalize it to the non-community flow. So let me just explain what I mean by non-community. So there's a theorem that I warned off. Which said that say for any x or t smooth over right, its direct category of Euclidean sheaves is equivalent to the category of perfect modules over some geometry. If x would be affine, this is still true, but that's a trivial result. You can take a on the left and a on the right. And so it also says that if x is not affine in the program, then that any variety is derived affine. Yes, and so then it's interesting to translate all these results to the level of this algebra A. So let me start from the beginning and try to translate the round homology. Try to rewrite the round homology in terms of so clearly A there are no economical ways to assign A to X. A is defined up to quasi-homomorphism and up to Morita equivalence. The first construction is quotient homology. And by definition, we are source in the category of modules between the diagonal bimodule and itself. That's the shortest definition, but there is also a canonical complex which computes. So for quotient complex, let me just write it down explicitly. Yeah, so, well, when I write the thing, well, actually A is a DG algebra, so this is itself a complex. So when I write it, I mean that I write it by complex and then take its total complex. So I hope there is no confusion. differential forms. So it's reasonable to call, well, if A is now just some associative linear algebra, it's reasonable to call Cauchy homology the non-commutative analog of the differential forms. So next, I want to have something like the Riemann homology. So question: can we recover the Riemann differential? Here just set side permutations of this tensor, and there is one at the end and at the beginning. So this formula doesn't seem very beautiful, but actually there is a very conceptual explanation of why it should be like that. But let me not go over this story. So yes, well, and that's the main properties. Position. Well, that first, that actually differential. Second is that it's actually differential not only on the level of terms, but it's actually a differential on the whole complex. So it commutes with B. Okay, so it maps in other direction. Yes, and the third one is that it actually answers the question at the beginning. So it says that if characteristic of K is greater, I think, than I plus 1, then we have the following commutative diagram. So it's isomorphic to differential forms, and here is one differential. It introduces something on Cauchy homology because it commutes with Cauchy differential. So, and so the diagram is commuted. Yes, well, here I don't need any assumptions on the characteristic of the base field, because to say that homology of Cauchy complex and differential forms it's true always, but in small characteristics it might be false that Cauchy complex is formal. But well, and so to prove the result like this, surely we'll need some formality. Really? Sorry, what? Oh, okay, but I don't know what to look for. Okay, so I don't know what to look for. Thank you. Okay. So you mean that for say non-prime varieties it will not do? tempting to just write down terms of the function complex with differential b. Oh, but actually, it gives the right answer. If A is smooth commutative, it's indeed the round homology. Compute the round homology. If we want to go further into the role of Digi algebras, we'll soon see that it's actually a wrong notion. So let me give one reason why. So yes, let's upgrade this constant Rosenberg theorem to this situation. So suppose I have some Digi algebra time from geometry. Then function homology of A. Yes, it's actually thing U minus P. So there is so how I can prove this statement? Just actually function homology is not an invariant of the algebra itself, but actually invariant of the category of modules array as a Digi category. And so if I have Q here and here.
Yeah, so it's P minus Q equals 5 because it's homological.
Okay, probably you're right. Yes, okay. Yeah, thank you. Okay, so if I use this definition, I get that just drum homology of X will be some homology of some differential on the level of these groups. So it seems like we get some term in the Cauchy-Drum spectral sequence, but certainly, in general, it doesn't have anything to do with drum homology itself. So we need to modify the definition a little. So actually, it helps to get just many copies of function forms. So I have this function differential, and I have this form differential. So let me just write into many copies of function complex, just zeros over the data. Yeah, so it's infinite in both directions. Well, I get the following y complex, then I take its rho and total. Okay. Now it's called periodic cyclic homology of my Digi algebra. Okay, so as usual, A is not just an algebra, but a Digi algebra, and all these are complexes, so we actually get some three-dimensional complex, and we should take sum totals in this direction and product totals in this direction. In a moment I will write down a slightly more explicit definition of this, if that's confusing. Okay, so this is called periodic cyclic complex, and its homology are called periodic cyclic homology. Yes, so now it's clear that it's not just some homology of some complex obtained from Cauchy's homology, but rather there is some spectral sequence of Cauchy's homologies which converge. So we actually get what we wanted. H, E, I, A. In this case, is equal to the direct sum over M. The homology M plus 2I. case bigger than 2 dimensions.
Just dimension.
Sure, you can understand. Yeah, so this is the restriction which I erroneously called it. Yeah, so, Paul, you may say that it seems that like I artificially added many copies of quotient complex, and I got many copies of Durand homology. But actually, it's very reasonable that we cannot obtain some non-commutative invariant which computes Durand homology itself, because everything, any reasonable invariant of the geometries which you construct in this form should be edited. So it should be a function from, say, the geometries. Of course, it should go through the G-categories, so to the vector space. But it should be edited. Namely, it should factor through K0 of the G-categories. But if I take a variety X and take a class of its direct category in K0 of the G-categories, it doesn't see even its Bethe numbers. For example, because direct category of P1 is just two direct categories of point. So there are no chance that I obtain some non-commutative kernel of the Durand homology itself. Okay. So now just let's try to construct a derivative analog for this theorem for periodic cyclic complex. Yeah. So first of all, I should say that there is this theory of Gauss-Line connection. Yes, it's due to Halezi and Getzel. That if I have, say, a H algebra A over some, maybe a fine base, just for simplicity, then it's periodic cyclic homology. That makes it a flat connection. Yes, our area before I was working over a base which was a field, and if you want to work over arbitrary rings, everything works exactly the same, but you should assume that your algebra is, say, generalized flat. So that the problem is exact. It's not wrong because the energy algebra admits semi-fluid motion, which has flat charts. So there is this flat connection, Sn. No, I'm not saying anything about the connection to the low point. Well, sure. Well, I think it's not true that there is a flat connection of the low point. Collision of version of the Swiss moment.
Yes, it's common, it doesn't affect the moment.
Yes. Well, but here's the problem is on the flat on the low homology. Well, it's actually. Yes, so this problem also can be seen trying to start a silicon homology, but I don't want to do wrong. Okay, so let me just write down what we would like to call non-commutative distance homology. So maybe just for the sake of time, I will change this. So we want to have by CP2 from the algebras over FP to, maybe just let's take the whole CP modules for the usual distance homology theory to obtain a reasonable theory of with ZP coefficients. We should also assume some programs on our variety, because otherwise the inverse limit is a wrong notion. first of all, prove it independently. So, in particular, it says that if we have two different liftings of pi-dg algebra over ZP, then their periodic cyclic homology are canonically isomorphic. So, let's prove this result just in a very special case. So, assume that we have a family of algebras, of DG algebras, over an affine line over ZP, DG algebra. And also assume that, that in this family, the multiplicative structure does not change. So, that it's just a great algebra structure is constant. And by placing special files. But differential deforms. Differential depends on G. Yes. And assume that I have two algebras. First one, say A0 is the final of A over 0, and A1 is final of A over T minus 2. These are algebras over ZP, but note that their reduction mod P are actually isomorphic. Because, here on, we have on A some differential, here, maybe sum of, say, dk, the power of t power of k. And so, here we have the differential just d0, and here sum of d k e to the power of k. So modulo p, the differential is just maybe, yes, sorry about that. I think I should ask you also the notion of the condition is complete. That's because I have everywhere here like infinite sums, and I want them to converge. So if I work over just z over pm, and of course there are nobody. But I want over ZP just for simplicity conditions. So A0 and A1 are a pair of liftings of this DG algebra to ZP, which are very, very special. They can be organized in a family over a line. So let's prove that their periodic cyclic complexes are quasi-isomorphic. How much time do you have?
15 minutes.
Okay. Yes. Let's use this Gauss-Meinl connection. So, I formulated it on the level of homology, but actually it exists on the level of complexity. This arrow is not just a genuine arrow of morphism of complexes, but it's a mapping to direct category. Sequence of complexes. And, on the level of complexes, I don't claim that it's flat. So, flatness in the direct category is somehow, not a straightforward notion for a connection. Certainly it should be stronger than just saying that square of the connection is 0 in direct categories. Probably we need to pick some homology between the square and 0, and also there will be some higher homologies. So I think that for the positive characteristic, I don't know how to see that it's flat in this sense. I think that's but anyway, we have at least we have a connection, and also we work here over a one-dimensional base, over a curve, any connections. Yes, and so we have this connection. Yes, okay, maybe just for completeness, let me briefly recall this if A itself would admit a connection which is compatible with the product structure, then everything will be trivial, but if A admits a connection which is compatible with product structure and differential, that means that this family is actually trivial. So for interesting families, there are no fault that there is a connection. But still, we can construct a connection which does not respect differential. So it's a map from just the underlying wave algebras. Well, at the beginning, I assumed that my family is trivial, so it's actually just some algebra over some algebra, great algebra over ZP. So I can take this trivial connection, F maps to D. Oh, but the problem with that, I think I have two different D's. Let's call it D drum. So the problem is that in general, it need not commute with the differential in the D junction. So, this connection, so it does not induce a connection with family D junctions. Well, but let's still try to construct a connection on periodic cyclic complex. So let's just try to write down CP or just this graded algebra. I forgot the differential. It gives a connection. Now, what does this thing has to do with periodic cyclic complex of the mighty algebra A sum? Well, as complexes, on terms of this thing and this thing, they're actually equal because they both are just there's a products of terms of A. But differential on this and this complex are different. So let me write how they differ. On CP direction, I have this quotient differential plus one differential. And on CP of my D algebra, I have also this, but also a part coming from the differential on the D algebra. Let me denote it by LD. So this is L stands for leader root. I will explain in a second why. Well, LD is just given by the label string. Oh, there's some Kashur sign. Also, this is just a definition of the differential of the bipolar. D has a degree 1, so I can just put 1 here, but I wrote it in the general form on purpose. So it just means that for any algebra A, its derivations act on periodic cyclic complex. Just by default. So the derivations need not have to be zero. What's the analog on in the it's actually X on CP and also on quotient complexes. So what's the analog of this in the community form? So A is again single community. Then just derivations are just vector fields on spectrum of A. differential forms and on the derivative. But in the differential geometry, we have a celebrated Cartan homology formula, which says that LV is equal to DIV plus IVD. And its formula is that derivations act by zero on the round homology. Actually, this is the case also in non-commutative form. So derivations, action of derivations by this LD actually are homotropic to zero on the periodic system. So let me formulate it precisely. Proposition. You can have any algebra, granting Q, and for any derivation B, is by algebra as always mean details. So there is so-called contraction ID. ID it's a map from terms of periodic cyclic complex. Commutator of function differential. Let me know D by delta with ID is LD. So this is exactly the same formula. Oh, and also in differential geometry we have some additional relations between contraction and with derivative. So actually, not all of them hold in the non-commutative form, and this is actually a huge problem. But let me write down one which holds, because if I compute with derivative with contraction, I get just contraction with respect to the derivative. Yes, so this is just proven by giving us this formula for ID. Okay, so let's, well, this was a diversion, but let's come back to our problem. So we have, we define connection on the terms, but it's not compatible with the differential. So the problem is that commutation of B plus B plus LD with nabla is not zero. So let's, question? So let's just twist a little bit our connection so that it becomes so that it commutes to this differential. So what do I mean by twisted connection? So connections on any module form a torsion or differential forms with coefficients in the endometer of this module. So I can, once I have one connection, I can just add any differential form with coefficients in endometer. So just all linear map from here to here. And we'll get other connections. So let's just add, say, put nabla GM, nabla plus, maybe I think minus, interaction with this B. So commutation of D and nabla is by definition D nabla minus nabla G. So this is the difference between two connections. So it's actually a differential form with coefficients in endomorphism with this C. Now it's also actually a derivation of my algebra A. So its contraction is defined and I can subtract it. So let's try to commute it with function differential again. First I get the commutation of this function on part with nabla, which is just zero because nabla is respective to the multiplicative structure. Second, I have commutator of LG with nabla. And finally, I have a commutator of this contraction with this whole differential. So, minus B plus C and D and B. Well, this is just L d number. And commutator of this thing with this thing is that by definition is also minus L d number. So this will cancel, and I also have a commutator of this and this, and well, the commutator is 0 because commutator of this and this is 0, and I apply this formula. So plus I commutator of d number, which is 0. So I get 0. So well, using this theory, I just shifted a little bit my connection, so I get a connection which is compatible with the form differential. This is what I want. Are there any questions about the construction? This is just a formal consequence of the existence of this open function. Actually, there is also analogous argument in community case equivalence. It was written by Bernoulli, which defines Gauss-Wien connection by just using contraction from differential equation. Okay, great. So I constructed a connection on a family of Dijon over a line. Sorry, on the very periodic cyclic mode. So what is, as I started, an important consequence of the existence of integrable connection with some model is the identification of infinitesimally closed fibers. So let's read it. I have connection CP. Okay. So it's parallel transport along it identifies. Just how it works in the differential geometry. We have a flat connection, then we have the points and the path between them. Then we can define parallel translation along gamma, which gives an isomorphism between fibers of my bundle with connection. But how to translate it into the our settings? Let's take a time to write thus. So there is a map, so T from CP of fiber A over 0 to CP of fiber A over P. So what happens? So I pick some S here, lift it to a section S tilde, lift it to a global section. Okay, so here slash means over and here means ocean. So, yes. And so what happens? I know the value of S tilde at 0. I want to compute its value. So it's called Taylor expansion. So put T of S should be the following sum. Yes. To the power of n, this S tilde, and it's all, it should be, it's an element here, and I should consider it as an element here. So just take its value. Yes, this is the formula, and know that, what I said about there was a pure manipulation, so I need to explain why this formula actually makes sense. So, a priori, this is just a rational number, and I want an element of CP. But the number of P in factorial or P in factorial is approximately in n over P minus 1. And here it goes as n. So there are actually, so it's not only well defined, but it actually tends to 0. So the series converges. So this is what means that I pick close enough points. So I don't claim that periodic cyclic homology of a fiber over 0 and over 1 are isomorphic, but only over points which have the same reduction 1. Okay, so this is the formula. time, but I think now to prove, to construct this CP tilde, it will be very easy. So actually, well, we haven't used one important structure on periodic cycle homology, which exists. Well, it's called multiplicative structure.
Sorry, so I read just reading that what I said that what you proved is that your periodic differential equation
Yes.
is trivialized.
Yes. It's
It's a complete number of solutions.
Oh, yeah.
The periodic differential
Prove the connection.
equation.
Just prove the connection to that. What do you mean?
No, it's just that, it's also trivialized. You showed that it's a complete set of solutions. You provided some solutions that you saw.
Oh, yes. Yes.
So you can identify fibers so that they.
Yes. So this was
Well, yeah, on the periodic disk or some periodic duality or some periodic.
Yes. Yes. Only. Yes. As I said, I construct transport on the controls.
Over this.
So there is actually an explicit formula of this general formula of the space of these flat sections, which was used by Kalevin to do this. But no, let's not talk. I mean, absolutely. Okay, so let's finish this. Yes, I said about some additional structure. The structure called is the multiplicative structure. So, yes, maybe I should say this earlier on. What are objects of each case are CP of A. Okay, so actually, if you remember, well, the complex which computes this complex was like translation where there was the stairs. So if I move my complex onwards, it doesn't change. So it actually has some action of Laurent series. So U means that this translation, and well, I have here Laurent series because I have taken the product of this complex, so it has. Yes, maybe it's not the right point to say that, but I'm just saying that CP of RT can only have a module over, not only over K, but over this Laurent series. Well, this just comes from this two periods. Okay, and so, yes, and I have a unit formula that CP of A or K transfer K of U, which is just CP of K over K itself. Transfer CP of K over K so it's isomorphic to CP of the identical. But now, if my A is a community geometry, then I have a map from A transfer A to A multiplication, which is a map of algebra. It's a map of algebra only at A is community. So I can compose it with a unit element. So basically, A. So I think for any community geometry, I have CP is not only of a complex of vector space, but it's also an algebra. Well, it's crucial here that A is community. Well, no, I mean complete it. Well, very well, yeah. Also for each element, it's not completed, but I think. Yes, but all the lights are very similar. It's very simple. So, yes, now I'm ready to just write down the formula for CP2. So I have a d-algebra A over F. I can consider it as a d-algebra over Z. Taking directly. It's no longer term-wise flat, so I need to pick some flat resolution. So let me not change my resolution, but I will just remember that I already should write directly. So let's consider CP of A over CP. And so as I said, you should, well, in the definition of this tensor product, you should integrate direct tensor product, or just replace A by some particular, or pick some resolution. So, well, we don't have any channel, let me just try to perform. I need to take, so this CP of A over CP is a module over CP of FP over ZP. Okay, so, well, as I explained here, this is an algebra, and also by Kuhn formula, I have an action of this on this. So this is an algebra, this is a module of this algebra, and I can just take tensor product of this with CP on CP over ZP, which is just Laurent's units in ZP. Okay? This is the definition. Sorry? Where? Over CP, it's CP considered over ZP, so that's the point. Yes, so right? Yes, when I write CP, say FP over CP, and let's just choose to break FP by some flat resolution. So exactly. So it lives in here. Huh?
What is it?
This is first of all, periodic second proportion.
No, the question is what is the fixed
Okay, well.
Maybe we should be
Okay, so like I said, I know what's called homology. Yes, magic 1 minute long.
Sure.
So
let you hear 3 minutes.
so I make it 3 minutes.
Yeah. Finish it only.
Yes, so let's. I'm sorry. The most interesting thing is to explain in what sense this is a module over this. I haven't explained this yet. So there are no morphic from this algebra to ZP. Here we should apply our thing with Gauss-Bonnet connections. So consider a family CP maps to ZP of T by T. This is a algebra over ZP of T. Its fiber over P is this one, and its fiber over 0 is ZP maps to ZP by 0. So, by our previous considerations, this is why this is a morphic. ZP over ZP maps to 0. And this algebra admits a map to ZP. So, this thing admits a map to ZP. Okay? So, here I will use all this theory of contraction of Gauss-Bonnet connections for the case of point. So, and now let me explain why this is actually lifting of periodic cyclic homology, or just because tensor A with P over ZP. So we need just to tensor everything here by FP. So we get CP of A tensor divided by tensor by FP of U, CP of FP and FP. And so again, by Kuhn formula, this is exactly CP of A over FP. And the potential